All right, we're going to finish up chapter 2 by just looking at some examples of finding more zeros of polynomial functions. So nothing really new from what we did before, except for we'll form some polynomials and just look at some more of the zeros as they come up. So one new thing we will add is we will formalize something that we've talked about quite a few times, and that is called the fundamental theorem of algebra. Now, there is the fundamental theorem of algebra, which is this theorem in algebra that kind of ties a lot of our polynomial zeros together. And it says this. It says any polynomial function, we'll call it f of x, has at least 1 0 in the complex plane, or in the complex number system. So this is kind of doesn't seem like a very important theorem because we've seen lots of zeros of polynomial functions. But this says any polynomial function I give you, it will have at least 1 0. So if I think of a polynomial function, let's say I think of it as x cubed minus 3x squared plus x minus 3, something like that, okay? Now, we know from what we talked about last section that this is degree 3, so there should be 3 zeros. But all this theorem seems to say is it says there is at least 1 0. Well, why this is still important is this does say there's 1 0, and let's say that 0 is whatever. Let's say it's a. So if this number gives me a 0, I plug in and I get 0, then I know that that is a factor of this, and then whatever I'll have left over is now a square with some other stuff. But the good news is now this is a new polynomial function, and it will also have a 0, so you can keep finding zeros of all these polynomial functions. So why this is important, it kind of leads to this kind of informal thing we said in the last chapter that we can now formalize. So a consequence of the fundamental theorem of algebra says any n-degree polynomial. So if there is an n-degree polynomial function, there is exactly n zeros. There are exactly n zeros in the complex number system. So basically we kept looking for these last time. We'd find the degree and try to figure out what they are. But the reason why this is true is the fundamental theorem of algebra. It's this theorem that says if you have an n-degree polynomial, if it's a 4th degree or a 5th degree or a 6th degree, that's how many zeros they are. There could be repeated zeros and have multiplicities, but in general, that has to be the number of zeros there are. So we're going to use this to find some different zeros and some different polynomials in this section. But other than that, really nothing too new. So one other kind of neat theorem that can help us, you've probably seen this as well, but we're going to kind of formalize it again. It's called the complex conjugate pairs theorem. Okay, it simply says this. It says if A plus BI is a 0 of f of x, so is a minus BI. So if you have some number plus or minus something I, so if this is a 0, then this would be a 0 as well. If this is a 0, negative 7i, this is like 0 minus 7i, then 7i is also a 0. So this is not really a complicated theorem because the way we get these imaginary roots is we'd either use quadratic formula, which has the plus or minus, or we'd use the square root principle where we get the x squared by itself and take the square root, where we add the plus or minus. So one way or another, you're always going to get those two answers, and they're always going to come in pairs. So this can help us out a lot when we're trying to find polynomial functions. So Here's an example where we're trying to find a polynomial function, and we'll see how this works. So this says, given a degree 5 polynomial function, so the fundamental theorem of algebra says there are 5 zeros, and we'll see which ones we know and which ones we have to find. What is the polynomial in both factored and simplified form? So we know the couple of these zeros. We know 2 is a 0, and we know 4i is a 0, and we know 6 minus 3i is a 0. So the other two zeros, since they're imaginary numbers that are unpaired, we'd have to find their conjugate. So 4i being a 0 means negative 4i is a 0 as well. 6 plus 3i being a 0, or 6 minus 3i being a 0 means 6 plus 3i would be a 0 as well. So writing this in factored form is really quite simple once you have these 5 zeros, just like we've done. We'll say this is x minus 2, this is x minus 4i, x plus 4i, I'm just putting them together, x minus 6 plus 3i, x minus 6 minus 3i. So this is done. This is my polynomial function in factored form. Now in general, this is how I would be fine with keeping it. I mean, this is a great factored form. If I wanted in simplified form, it would be a little trickier because in simplified form, we'd have to multiply this all out. I don't expect that I would ever do this to you on a test or anything, but I think it's worth doing at least once just to show you when I do simplify this all out, I do get a polynomial function with no imaginary numbers. So even though the zeros are imaginary numbers, the original polynomial in standard form is not. Just like we saw before. We had numbers that had no i's in it, but its zeros had i's. So what I'll do, if I was going to simplify this, I would probably multiply these two that are conjugates. So that's fine if we do that. So I'll just leave the x minus 2 here for now by itself. Now if I FOIL these two, x times x is x squared. X times 4i is 4ix. 4i times x is minus 4ix. And this is going to be minus 16i squared. So I FOILed it out. And I'll do the same thing for the second two. Now there's 3 things, so it's going to be a little trickier. We're going to multiply x to all 3 terms. So x squared. And then x times negative 6 is negative 6x. And then x times negative 3i is negative 3ix. Then I'll multiply everything by negative 6. So I have minus 6x plus 36. And then plus 18i. Again, that's just doing the negative 6 times anything. And then I'll do the 3i. So I get plus 3ix. That's just going here. Minus 18i. And then minus 9i squared. So that's a lot of foiling. But good news is a lot of things will clean up when you do this. So this is x minus 2. The 4ix's cancel out. And if you recall, I squared from algebra 2 says I squared is negative 1. So that I squared is just negative 1. So negative 16 times negative 1 is positive 16. So do you notice when I FOIL that, all the i's go away? And that's going to be true in this next one as well. Because if you notice, we have negative 18i and positive 18i. We have positive 3ix and negative 3ix. So a lot of the stuff with i's is going away. So we have x squared minus 6x is minus 12x. And then again, this negative 9i squared is negative 1, so that becomes positive 9. 36 here and positive 9 here is 45. So now we just keep going. So we can keep multiplying. Now all the i's are gone, but if I wanted in simplified form, I could keep foiling it and distributing. So I think the easiest way is I'll just multiply these two together next. And you start to see why we don't want to do this on a test or something. X times x is x squared minus 2x squared plus 16x minus 32. if I multiply this, x squared minus 12x plus 45. And now I'll do the same thing. I'll multiply again. I'll multiply the x cubed to everything. So I'll do this one, the x cubed times x to the fifth minus 12x to the fourth plus 45x cubed. I'll do a different color for the negative 2x squared. So negative 2x squared times all of these things is going to give me negative 2x to the fourth. That's a 12. Got to be super careful with these. Negative 2x squared times negative 12x squared is 24x cubed. Negative 2x squared times 45 is negative 90x squared. Now I'll do the 16. So that's going to be positive 16x cubed. So 16 times negative 12 is negative 192x squared. And then we're going to have negative 16 times 45, or 16 times 45, which is some big number, 720 plus 720x. But now I'm not done because I still have to do the last term, which is this negative 32. So I'll just do that on the next line, although it's one big thing. So then we'll have minus 32x squared. Negative 32 times negative 12 is 384x. And then negative 32 times positive 45 is negative 1440. So as you can see, this is going to be a large polynomial, x to the fifth. I have 2x to the fourth, it looks like. Minus 12 minus 2 is minus 14x to the fourth. I'm just going to cross out once I've done them. 45x cubed. 24x cubed, so we have 45 plus 24 plus 16 is 85, so we have plus 85x cubed. And then we have negative 90 x squared minus 192, and then a negative 32 as well, which is negative 314x squared. That's all my x squareds. So it's really just a foiling problem at this point, but it's a huge, huge, huge foiling problem. So 1104x minus 1440. So this is my polynomial function. This is my polynomial function in standard form. So obviously, this is in factored form up here, which is pretty nice. And this is the expanded form. We generally do not love the expanded form just for this reason. Okay? So this is a polynomial function that has those 5 zeros. Now the only difference would be is what if I wanted a different y-intercept? Well, I can certainly do a different y-intercept because if you think about it, I can multiply this polynomial function by some number a and it would still have the same number of zeros. So if you wanted a different y-intercept, the a value would change. We're not going to figure that out, but just something to remember. Just because something has zeros, if you stretch or compress it, it'll still have the same zeros because 0 times anything is still 0. So if you can do it in factor form, that would obviously be a good thing. But if you need to do it in a different way and FOIL it out, you certainly could. All right, so the other thing we'll do in this section is we'll just keep working on finding the zeros of polynomial functions. We'll expand this. We'll have some more that have some of the complex roots, so imaginary solutions. We'll finish this up. So if you look at this one, this polynomial function x to the fourth minus 1 has 4 because it is a degree 4 polynomial, so there should be 4 of them. Now, if I talk about the possible rational roots, or possible rational zeros, the p over q, well, p in this case is factors of the constant, which is 1, and q is factors of the first number, which is also 1. So if I do P divided by Q, I just get plus or minus 1. So the only ones that work are plus or minus 1. So obviously what I'd like to do is I would like to graph this and see which of these works. So if you graph it, and I think you should graph it, then I get something that looks like this when I look at my graph. Looks something like this. So this actually passes through both of those. So -1 is a valid 0, so is 1. Now we still have 2 of them missing. They could be a repeated root, it could be 1, 1 again, or they could be imaginary. So what I'll do, just like I did in the last section, we'll divide out the ones we know. So we'll start with -1, or I could start with 1. I just happen to do this one. 1, no x cubed, no x second, no x to the first, but then there's a constant of -1. Now if I've done this right, we should obviously have a remainder of 0. So 1, -1, -1, 1, 1, -1, -1, 1, and 0. So we had a 4th degree equation. I divided out by the 0 of -1, and I have this 3rd degree polynomial equation left. Not very helpful to us because we don't really have a lot of ways to deal with that. So what I'll do is I'll ignore the remainder, and now I'll divide out by the other 0 I know. And you could have started with 1, it doesn't really matter. Bring down the 1, 1 times 1 is 1, -1 plus 1 is 0, 1 times 0 is 0, 1 plus 0 is 1, 1, and 0. So now again, the cool thing is this is a quadratic. So this is 1x squared, no x's, plus 1. So my other 2 zeros are hidden in this quadratic. So I'm going to figure out when is x squared plus 1 equals 0. Now, you can do this lots of ways. You could do quadratic formula. It's not the way I would prefer to do it. I would prefer just to subtract 1 from both sides and then take the square root. Because if you don't have an x, just use this square root property. So x equals plus or minus, because when you take the square root, you add the plus or minus. And the square root of -1 is just I. Because if you ever have a negative square root, it's an I, and then the square root of 1 is just 1. So my other 2 zeros are I and -I. So those are my 4 zeros. 2 real, 2 imaginary. Now this problem doesn't ask for it, but I could certainly write this in factored form if I wanted to. I could say g of x equals x plus 1, x minus 1, x plus I, x minus I. Again, not something that you have to do, but you are welcome to do that. And the problem could ask that as well. Now if I look at the next one, we got another polynomial equation. This one only has 3 roots because it is degree 3. So we have 3 zeros, 1, 2, and 3. And I'd like to figure out what those are. Now again, I'll go through the same routine I did earlier. So I'll ask what are possible rational zeros. A lot of you will go ahead and right away go to the graph. Not necessarily wrong, but just so I know what I'm looking for, I'll do the possible rational zeros. Now Q in our case is just plus or minus 1. So that's pretty simple. And then 85 is 1 and 85. And then it divides by 5, 5 and 17. So there's really not a ton because when you divide them all by 1, you just get these 8 zeros. Now again, I guess you're not going to graph these, you are going to graph them, you're not going to plug them in. So if I graph it, and again, I suggest you do take a look at what this looks like. When I graph it, it looks something like this. And the only one I see is -5. All right? But again, graph it on Desmos, graph it on your TI calculator, verify that this graph is what you see. So -5 is the only 0 that I see. Now, could the other ones be -5 as well? Possibly. Could they be complex numbers? Possibly. Well, the only way to find out is really to divide and see what we get. So I'll put -5 on the outside, 1, 13, 57, and 85, and then we'll divide out. 1, negative 5, 8, negative 40, positive 17, negative 85, and 0. So we get 1x squared plus 8x plus 17. And so that quadratic, when I set it equal to 0, has my other two missing zeros. So we know it's not going to factor, because if it was going to factor, we would have found more nice ones on the graph. It's not like the other one where I can just move the 17 and take the square root because I have the 8x. So really my only option is to do quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. So opposite of b is negative 8 plus or minus the square root of 8 squared minus 4 times 1 times 17 all over 2 times 1. So that's where I'll find my other zeros. So I'm going to start by just taking a calculator and multiplying everything inside this square root. And so when I do that, I get negative 4. So this becomes negative 8 plus or minus the square root of negative 4 over 2. Now, the square root of negative 4 obviously has an I. It is a negative square root, so it has to have the I. And the square root of 4 is just 2. So this is negative 8 plus or minus 2i over 2. I because it's negative, and then the square root of 4 is just 2. So you can see that these all can divide by 2. So to finish up, I'll just divide them all by 2. So I'll get negative 4 plus or minus 1i, or just plus or minus I. So my other zeros are minus 4 plus I, minus 4 minus I. So those are my 4 zeros. Which kind of makes sense based on what my graph is, because it only crossed once. The other two zeros, if they're not x-intercepts, they have to be imaginary. So you're going to divide out. You're going to get a nice one like the first one where you can just do square root property, or something where you have to use your quadratic formula like we did here. Okay, let's take a peek at one more. So we have this large problem where we have a degree 4 polynomial. So if it's degree 4, I know there are 4 zeros. 1, 2, 3, and 4. Now we want to find those. I'll do the same process. So I'm going to say my p's are 65 and my q's are 2. And again, some of you are already on the graph, and that's okay, but the possible rational zeros, so my p's, what multiplies give me will be 1 and 65. And let's see, 5 and 13, and I think that's it. Now my q's are factors of 2, which are just 1 and 2. So I'm going to take everything on this list and divide it by 1, and then everything on that list and divide it by 2. So I'll get 1, 65, 5, and 13, and then I'll divide them by 2. 1/2, 65 over 2, 5 over 2, and 13 over 2. So we have quite a few zeros in this case, quite a few to investigate and see if any of them are zeros. So when I graph this, and again, pull up your Desmos, pause the video, graph this, I get this basically this huge parabola that goes down forever, and then it kind of goes back up forever. It's pretty skinny. But there are 2 x-intercepts I see, and this one appears to be at 1/2, and this one appears to be at 5. Both of those are on my list, so I'll say 5 and 1/2 are both valid ones. And I'll just kind of go through this process, okay? So I know the remainder will be 0 for both, so I'll divide it out. I'll start with the half, I don't know, just get the fraction out of the way. You could certainly start with the 5, doesn't matter. 2, 1, negative 35, negative 113, and 65. So that's 2. Half of 2 is 1, which gives me 2. Half of 2 is 1, which is negative 34. Half times negative 34 is half of negative 34, which is negative 17. So that's going to give me negative 130, and half of negative 130 is negative 65. So it works out really nice. Now, you could have started with the 5. Maybe it would have been easier, but this wasn't too bad. I'll ignore the remainder. Now I'll divide out by 5. So 2, 10, 12, 60, 26, and then 130 and 0. Now this one's a little interesting. So this is 2x squared plus 12x plus 26. And I want to figure out when that's equal to 0. Now, you can solve this with quadratic formula right now. It's 100% will work every time. But just to make my life easier, if you notice, all of these numbers are even. So I know if I divide them all by 2, it will all work out really nicely. And I can do that because the other side is just 0. So I'm trying to figure out where it's 0, so dividing is really not a problem. So I get x squared plus 6x plus 13 equals 0. You could definitely use the 2, 12, and 26 in your quadratic formula. It would just be larger. So I just chose to simplify it. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. And I'll just plug them in. So negative 6 plus or minus square root 6 squared minus 4 times 1 times 13 all over 2 times 1. Now if I plug that in the calculator, so I'll do the inside first. 6 squared minus 4 times 13 is negative 16. So negative 6 plus or minus square root negative 16 over 2. So square root of negative 16 is I, and it would be 4i, because the square root of 16 is 4. And then just like last time, just divide them both. So negative 3 plus or minus 2i, because you're just dividing both of these by that. So we got negative 3 plus 2i, and negative 3 minus 2i. So same process for all these. So hopefully nothing too radically new from what we did in the last section. If you have questions, though, please let me know.